Hello, this is the luckiest maths teacher in the world. Thank you so much for tuning into this video in which we will look at factorials and arrangements. So factorials are very important in combinatorics. Combinatorics is all about counting tools and factorials help us count. So the factorial symbol is this exclamation mark. So n factorial is each of the positive integers up to and including n multiplied together. By definition, 0 factorial is equal to 1. So for example, 4 factorial is just 4 times 3 times 2 times 1. It obviously doesn't matter whether I write 1 to 4 or 4 to 1 because the order of multiplication doesn't matter. So 4 factorial, if you multiply them together, is 24. So how would I simplify this? Well, 500 factorial is bigger than can be stored by most calculators, but we can solve this. See, 500 factorial on top is 500 times 499. It's each of the positive integers all the way back to 1 multiplied together. So 499 factorial, we just start at 499 and we go all the way to 1. So I can cross out these and these. I can cross out anything on the top and bottom as long as it's being multiplied. So even though my calculator can't tell me what 500 factorial is, 500 factorial divide 499 factorial will just be 500. All right, let's solve a more complicated problem, this here. So this one's a bit tricky because I can't just cross things out because I've got a plus here. You can only cancel factors, things being multiplied on the top and bottom of a fraction. But no need to worry, what I can do is I can factorize the bottom. See, each of these terms here and here has a common factor of 297 factorial. So what do I times by a 297 factorial to get 297 factorial? Well, that's just 1. What do I times by 297 factorial to get 298 factorial? Well, 297 factorial is all the numbers 1 to 297 multiplied together, so you just need to multiply by a 298 to get 298 factorial. So what we have on top is 300 times 299 times 298 times 297 all the way back to 1. And on the bottom we have, so this number here is 299, and then we're timesing by 297 factorial, which is 297 times 296 all the way back to 1. So I can cross out now anything that's being multiplied. I can cross out 297 factorial and 299. So the final answer is 300 times 298. Okay, so that's what factorials are and how we can manipulate them. Let's now look at using them to count arrangements. So this is how we calculate the number of linear and circular arrangements, both involving factorials. So let's go through an example to elucidate what this means. So how many different ways can we arrange 3 students? So we'll just call the students A, B, and C. So how many ways can we arrange them in a line? Well, we could have A first, then B, then C. We could have A, C, B. Each of these that I'm writing in red is an arrangement, and the order matters. The same objects in a different order are counted as different arrangements. So in a line, there are these 6 arrangements. So that was easy because there were only 3 students. Of course, if there were like 20 students, it would take forever to write out each of these. So the quick way to do this is we just write 3 factorial is 6. It was 3 factorial because there were 3 objects to be arranged in order. 3 factorial is just 3 times 2 times 1, which is 6. And the 6 possible arrangements are those here. All right, but what about if we arrange the students in a circle? It turns out we get a different answer. So why is that? So we can still write out 6 potential arrangements, A, B, and C. But the thing is, if they're in a circle, I can rotate to get the same outcome. So if I wrote 120 degrees this way, I'll have the B up here, the A here, and the C down there. And then I could rotate 120 degrees again. I'd get the C here, the B here, and the A there. Each of these is considered the same arrangement. The reason is, in all three of these cases, A has B to their right and C to their left. A has B to the right and C to the left. Similarly, in each of them, B has A to its left and C to its right. That's why they are considered the same arrangement. So the other way I could do this is I could have A here, C here, and B there. That's considered a different arrangement because now we have B to the left rather than the right of A, and C is to the right. But similarly, I could just rotate this 120 degrees. I could get C up here, A there, B there, and if I rotate it 120 degrees again, I get B here, C here, and A there. Once again, all three of these are considered the same arrangement because in each of them, we have C to the right of A and B to the left of A. So how many ordered arrangements are there if the three students are arranged in a circle? Just two. Basically, we took our 6 arrangements, but we divided by 3 because we could rotate the circle this many times and get the same arrangement. But 3 factorial divide 3 is just 2 factorial. In fact, that works similarly for any n. N factorial divided by n is just n minus 1 factorial. That is how we get the formula for circular arrangements. You have the same n factorial linear arrangements, but you divide by n because you can always rotate the circle and come up with an arrangement that is considered the same. All right, let's now look at some more challenging questions. So we're going to look at how many arrangements are possible if 15 students are sat in order, but Aiden, Ben, and Charlotte must sit next to each other in any order. We're going to figure out how many ordered arrangements are possible if firstly they're arranged in a line and secondly arranged in a circle. So just note here that when I say they can sit in any order, I mean it doesn't matter if it's Aiden, Ben, Charlotte, or Aiden, Charlotte, Ben, but the overall ordering of all 15 students does matter. So let's first look at how many ways we can arrange them in a line. So if these 3 have to be together, we treat them as one block. It's almost like we treat them as one student. So that's one student, and then we have to arrange the other 12 students. So basically there are 13 entities or 13 students here that we have to arrange. The number of ways we can do that in a line is 13 factorial. But we now have to consider for each of these 13 factorial arrangements how we can order these 3. The way that we can order 3 students in a line is 3 factorial. So that's very similar to the problem we did on the previous slide. 3 items you want to arrange in a line. There are 3 factorial or 6 ways to do it. So we're saying for each of these, there are 6 ways that we can arrange Aiden, Ben, and Charlotte. So we multiply these 2 together. So 3 factorial by 13 factorial is a really large number, and you can just leave your answer like this, or perhaps you like to put it in scientific notation. So note, factorials get large really quickly. As this number for which you're taking the factorial increases, the whole answer gets big very, very quickly. All right, let's look at B. So B, this time, we're going to arrange them in a circle. So remember that that's very similar, but there's one thing we have to change. Now, there are still 3 factorial ways to arrange Aiden, Ben, and Charlotte, but we multiply by n minus 1 factorial, 12 factorial. Here we've still got like 13 students, treating these as one student plus the other 12. We've got 13 students. The way to arrange 13 students in a circle is 12 factorial. So here again we get a very large number. It's around about 2.9 billion. So it's not uncommon when you're counting arrangements using factorial to get extremely large numbers as your answer. All right, thank you so much for tuning into this video. This has been the luckiest maths teacher in the world. Have a great day.